So we have discussed covariance variance matrix. Then we have discussed as an example we have discussed the discrete type random variable. Now we are going to discuss one continuous type random variables in which we can describe the covariance variance matrix in a nice way. That is one very important multidimensional random variables of continuous type that is called multivariate normal distribution, which has a lot of applications. The way the central limit theorem, which we are going to discuss later, which has a lot of applications in the real world problems, the same way the multivariate normal distribution also going to play important roles in many complicated problems in probability. Let x be a vector whose elements are x1, x2 and so on. It is a n-dimensional random variables are of continuous type. With each random variable x size follows a normal distribution with the mean mu I and the variance sigma I square for I is equal to 1 to n. Then we call the random variable x as the multivariate normal distribution. Whenever each random variable is normal distributed random variable, then the n-dimensional random variable is going to be called it as a multivariate normal distributed random variable. Then we can define the joint probability density function. The joint probability density function of the random vector capital X whose elements are x1, x2, xn is given by x is the vector, that is 1 divided by 2 pi power n by 2 multiplied by the determinant of the covariance variance matrix, the whole power minus 1 by 2 multiplied by exponential of minus 1 by 2 x minus mu multiplied by the covariance variance matrix with the inverse multiplied by x minus mu the whole transpose, where the mu is a vector, that is a expectation of the vector. That means whose element are expectation of x1, expectation of x2 and so on. The nth element is expectation of xn. Mu is the vector whose elements are the individual expectations. And summation is a positive definite matrix. It is the covariance variance matrix of the n-dimensional random vector x1, x2, xn. That means whose elements are, the diagonal elements are variance and off diagonal elements are covariance between any two random variables, which is denoted by sigma 1 2. Since sigma 1 2 is same as sigma 2 1, so both we are rated as a sigma 1 2 and the last element is sigma 1 n. Here the first element is sigma 1 n, where sigma I j is nothing but the covariance of x I with x j. When I and j are same, then it becomes a variance of I, variance of the random variable xi. So the joint probability density function can be written in the form where mu is the vector and sigma is the matrix, and similarly small x is also vector. For example, when n is equal to 2, we call it as a bivariate x as elements x1, x2, that is called a bivariate normal distributed random variable. We call it as a bivariate normal distribution. In that case, the mu is going to be mu1 comma mu2, where mu1 is nothing but expectation of x1 and mu2 is nothing but the expectation of x2. And the summation matrix, that is covariance variance matrix, is nothing but variance of x1, covariance of x1 x2, covariance of x1 x2, and variance of x2. That is sigma 1 square covariance of x1 with the x2, covariance of x1 with the x2, and variance of x2. Now the joint probability density function will be much simplified. That is f of x1 comma x2, whose elements are x1 x2, that is nothing but 1 divided by 2 pi power n by 2, n is 2 here, therefore 2 pi, and determinant of sum matrix raised to the power minus 1 by 2, and exponential of multiplied by exponential of minus 1 by 2 x minus mu summation inverse x minus mu transpose. So we will find out each quantity separately. Determinant of summation matrix, if you simplify, you will get sigma 1 square, sigma 2 square, and the covariance of x1 x2, since we have only 2 elements, we can make it as a row, therefore it is going to be 1 minus rho square. Similarly, if you find out the inverse of covariance variance matrix, that is going to be 1 divided by variance x1 x2 multiplied by 1 minus rho square multiplied by rho is the correlation coefficient, correct, sigma 2 square minus sigma 1 2, that is covariance of x1 with x2, minus x1 with x2 sigma 1 square. Therefore, you substitute in the joint probability density function, therefore f of x1 with x2, that is going to be 1 divided by 2 pi sigma 1 sigma 2 multiplied by square root of 1 minus rho square exponential of minus 1 by 2 times 1 minus rho square multiplied by x1 minus mu1 divided by sigma 1 the whole square minus 2 times rho x1 minus mu1 x2 minus mu2 divided by sigma 1 sigma 2 plus x2 minus mu2 divided by sigma 2 the whole square. This is in the curly bracket, this closed bracket. So this is the joint probability density function of a bivariate normal distribution, in which each one is a normal distributed with the parameters mu1 comma sigma 1 square. Here there is another observation. We are not making the assumption of both the random variables are independent. If they are independent, then the correlation coefficient becomes 0, then we would have the middle term. So this term will vanish. So you will have first term as well as the third term. Similarly, when the rho square becomes 0, then square root of 1 minus rho square won't exist. So when they are independent random variable, then easily you can write as the product of a two probability density function of a normal distributed random variable. But if material of both the random variables are independent, we can get the marginal distribution of the random variable x1. From the joint you can always get the marginal by integration with respect to the other variable, that is minus infinity to infinity the joint probability density function of x1 x2 with respect to x2. If you simplify, you will get the answer, that is 1 divided by square root of 2 pi sigma 1 exponential of minus 1 by 2 x1 minus mu 1 divided by sigma 1 square. So this is the marginal distribution of the random variable x1. Similarly, you can find the marginal distribution of x2 by integration with respect to x1 of a joint probability density function. So that is going to be 1 divided by square root of 2 pi sigma 2 exponential of minus 1 by 2 x2 minus mu 2 divided by sigma 2 the whole square. By seeing the probability density function, you can make out this is a normal distribution with the mean mu1 and the variance sigma 1 square for the random variable x1. Similarly, for the random variable x2, it is also normal distributed with the mean mu2 variance sigma 2 square, whereas the joint one is given as this is the joint probability density function of bivariate normal distribution. So this is a very good example of how the covariance variance matrix play a role. So we have discussed earlier in the discrete type. Now we are describing the continuous type random variable as an example for describing the covariance variance matrix. There is another important observation in the joint probability density function of normal distribution. If you substitute rho equal to 0, that is a correlation coefficient equal to 0, you will get the first term and the third term. In that we can come to the conclusion, you will get joint probability density function of x1 x2 is same as the product of probability density function of x1 x2. That is when rho is equal to 0, the joint probability density function of bivariate normal distribution is lambda up the probability density function of a normal distribution in the product. This is a very important result in the sense when rho is equal to 0, that is a correlation coefficient is 0, we are getting an independent relation. If they are independent, then the joint probability density function is going to be the product of probability density functions. Usually or in general, the correlation coefficient is 0, that does not imply they are independent random variable, whereas independent random variable implies the correlation coefficient or covariance between any two random variables going to be 0. The converse is not true in general, but for the normal distribution the converse is also true. That means the covariance between any two random variables or the correlation coefficient between those two random variables are 0 implies those random variables are independent. So this is a very important result. The if and only if condition for the correlation coefficient is 0 and independent are going to be satisfied only for normal distributed random variables.